So welcome everyone to our December 10, 2025 session for Cohere for AI for the computer vision community. My name is Amit Taylor, and I am one of the leads for the computer vision community. And I'm also joined today with our co-lead, Benedict. Benedict, if you want to go ahead and introduce yourself.
Hello, everyone. The name is Benedict, and I co-lead the computer vision group at Cohere for AI with Amit, where we do interesting stuff. We talk about latest research. We discuss interesting trends in the field of computer vision. And of course, we hold sessions like this where we invite guest speakers to share their wide spectrum of knowledge with us. So without further ado, I will turn the reins back on into Amit's capable hands, and then let's see what we have for today. So Amit, please fire away.
Okay, sounds good.
Yeah.
So for those of you who are new to Cohere for AI, if this is your first call, first of all, welcome. We're happy to have you here. I just wanted to spend a couple of minutes before we got into our main topic or our main presentation today to explain a little bit about Cohere for AI. Cohere for AI is a hybrid research lab and open research community that's dedicated to contributing fundamental research in machine learning. And Cohere for AI works to solve some of the field's most challenging problems. And more importantly, as you'll see on the next couple of slides, Cohere for AI, one of its main goals is to create more points of entry into machine learning research. So you'll see that throughout a number of the programs and events that Cohere for AI offers. It always goes back to the overarching theme of creating more points of entry into machine learning research. So with that being the case, one of the biggest events, of course, that we have in the machine learning industry is NeurIPS, which everyone's pretty well aware is kicking off in about another hour in Vancouver. It runs through December 10th through 15th. So Cohere and Cohere for AI is usually very active at NeurIPS. And this is one of the events where you really get to see, a number of the researchers from Cohere for AI and from Cohere, presenting their research at this event. So just wanted to give you a quick idea of some of the sessions that you'll see at NeurIPS this year. Let me change my presentation mode here. One moment. Okay, so we have a number of presenters from Cohere and Cohere for AI this year. To give you an example of some of the main track publications that you'll see this year, they run the gamut from NLP, to computer vision, etc. And again, these are all presenters who are either Cohere employees or are researchers via Cohere for AI. And we have a number of sessions on December 11th and December 12th for main track. And then there are a number of workshops that are being run at NeurIPS from Cohere as well. Starting today, either run by Sarah Hooker, who is the lead of Cohere for AI, up to a number of the researchers at Cohere. So again, this is sort of a culmination of a lot of the research events and research activities that Cohere has throughout the year. During the course of the year, many of these individuals go on to present their research, at events like NeurIPS. So just wanted to make everyone aware of that. And one thing I will mention for NeurIPS, after the events, they ordinarily present a URL or a website where you can go and view the presentation. So all of these presentations from Cohere and Cohere for AI will be available after NeurIPS. I think sometime in January, they make the link available. Okay, so again, that is one of the key events that we do during the course of the year. In terms of computer vision, I just wanted to give you guys an idea of what's coming down the pike, at least in early January or early first quarter 2025. We had a number of presentations this year. I believe we had about 12 to 13 presentations or so this year. But with this being the last of the year, we're at our last presentation today, and just wanted to give everyone, especially those of you who are new, an idea of what's coming in the first quarter of next year. So we have a wide variety of sessions. In January, we'll be kicking off with Nico Misenkoma, who will be talking about data-driven feature tracking for event cameras. So that'll be a very interesting session in January. In February, Alexander, who's from Oxford and Google DeepMind, he'll be presenting on shape image correspondence with no key point supervision. So that'll be very interesting in February. And then in March, we have a really interesting presentation that you don't really see too often, at least in terms of machine learning. But we'll have Mike Walmsley, who is an astrophysicist at the University of Toronto, and he'll be talking about scaling laws for galaxy images. So I will definitely attend this one because I am very much into aerospace. So this will be a very interesting session. So throughout the course of the year, we usually have a session, 1 to 2 sessions per month. So as we proceed through the beginning of next year, we'll give you more information about upcoming sessions. Okay, so finally, with no further ado, let's go ahead and focus on our presentation for today. So today I am happy to introduce our guest speaker. Our guest speaker today is Kirolos Ataallah. Kirolos is currently a computer vision engineer at CreativAI. His research lies in computer vision and video analysis, specifically through the use of multimodal large language models. Kirolos spent about a year as a research intern at KAUST University. In 2023, he completed his master's degree in AI and data science at Ottawa University in Canada. And in 2020, he earned his bachelor's degree in computer engineering from Shoubra Faculty of Engineering, Benha University in Egypt. So with that being the case, with no further ado, I'm going to go ahead and segue to our guest speaker, Kirolos. Let me stop sharing Kirolos. Okay.
Yeah, hello everyone, and thanks Ahmed for this introduction.
Okay.
So yeah, let me share my screen. Can you see my screen now?
Yes, we can.
Okay. So I'm Kirolos Ataallah, and today I will present the Goldfish paper in long video analysis. So this paper has been accepted in ECCB 2024, and I implemented this project during my internship in Ottawa University under the supervision of Professor Mohammed Husseini. And also we have a collaboration with Professor Jürgen Schmidt-Cooper Group and some teammates, Sam Suleiman from Harvard University. He is one of the teammates that's collaborated to this project. So let's start by today's agenda. In this session, we will start with the introduction and the opening statement, then move into the what the challenges in long video, and what is the TVQA-long, and what is the architecture of mini-GPT video, and how we trained it, and what is the dataset that is used to training this model. Moving to the Goldfish framework and the paper results. And finally, we have the applications study and qualitative results. And finally, we have the summary of the paper contribution, and we have 10 minutes for questions and answers. So let's start, but the question is, why is it called Goldfish? Okay. So the common thing between the different type of fish is that they have very, very short memory, like just a few seconds. But there are a special type of fish called goldfish, and this type of fish have a remarkable memory, which lasts just for 2 months, okay? Which can last for 2 months. So inspired by this goldfish, we decided to name our model as a goldfish, because it can remember different events through the video. So what is the problem statement to this paper, or we are talking about today? This paper is for video question answering, like how the AI model can understand videos and answer specific questions about it. And also, we did a step to solve some of the long video understanding challenges through an efficient retrieval mechanism. So what is the challenges in long video understanding? What makes it difficult? First, we define as 3 challenges. So first, it is the noise and redundancy, as long videos often contain irrelevant or redundant information, making it challenging for the current LLMs to extract the meaningful information from these heavy or too many tokens for the videos. Also, the second challenge is the limited context window for LLMs, like most of the video LLMs have a limitation, or most of the LLMs themselves have a limitation in the context window, like Llama 2 have only 4K context window, and so on. So most of the current models have a maximum in the number of frames. Okay, so each we have a limitation in the input number of frames to the video LLM. This is the second challenge. And the third challenge is the lacking of benchmarks for long video understanding. Okay, so nowadays we have some recent long video benchmark, like video MME, long video bench, MLVU, LV bench, and Infini bench, and so on. But all of these new benchmarks appeared for released in June 2024. And by the way, this project submitted to ECCV in March 2024. So while implementing this project, there is no existing of long video benchmark. So that's why this motivated us to think about what is the easiest way to have a long video benchmark without collecting the videos or have an annotation, because doing this will take a lot of time. So we did a trick to an existing data set to convert it from short video evaluation to long video evaluation. So how we did that? We searched for a data set and found that TVQA is the best one that can fit. So TVQA, it is a data set that have a large scale from videos and QA. And this data set based on 6 popular TV shows, like Friends, Big Bang Theory, and Castle, How I Met Your Mother, and so on. But in this data set, in the original version, it have a clip, has many clips, and each clip for 1 to 2 minutes in the duration. Okay, and each clip have some questions about it. Okay, so what we did is we concatenated the related clips from the same episode together to finally have the full episode with some questions about it. Okay, so TVQA-long, after this concatenation, we found that the video duration converted from just 1 to 2 minutes to 30 minutes, and we have a set of questions about this or for this episode. Okay. So comparing to the existing benchmarks there in March 2024, so we tried to our best to collect or to know more about the existing benchmarks in long video. Like we found Movie QA, and Movie QA originally it is a short video benchmark that is released in 2016. And unfortunately, this benchmark not available now. Only the available is the JSON annotation, not the videos itself. Okay? And by the way, the videos itself, it's a clips with an average duration of 4 minutes. Okay, but we did a trick, another trick, to we searched for these movies. Okay, because we have the annotation, so we searched for the movies, and we found that there are another data set called the MovieNet, and MovieNet fortunately have 1,000 movie. Okay, and we found that there is an overlap between the MovieNet movies and the movie QA annotations with an 30 movie, okay, with 1,000 questions. But the point here is that these questions is about the movie plot, not vision questions, or not this data set or this benchmark doesn't contain a vision question. And what I mean by vision question here is that it's a question like what is the color of Ross's T-shirt in this video, or what is Chandler holding in his hand when he is talking with Ross, or something like this. Okay, but the question, the movie plot question, like why Joey is sad. So why Joey is sad? This is maybe because Phoebe. These are the characters and Friends. Okay, so because Phoebe told him bad news or something. So these questions can be answered from the subtitles or something. Okay. Also, we found the LlamaVid project, and this project is a concurrent project with Goldfish. Okay, but unfortunately, this project, even this project or this model can have the capability to process long videos, but the paper itself doesn't contain any evaluation for the long video. Okay, but the good thing is that the authors of LlamaVid trained their model with data. They call that LlamaVid data. Okay, and to have a signal to evaluate our model or to compare between Goldfish and the LlamaVid and so on. So we split this training data of the LlamaVid model, okay, into 90% as a training data and 10% as validation data. And we found that there is 79 movies, and with 900 questions. Okay, but also these questions is for the movie plot, because it's generated from the text content, like the summary or the transcript of the movie. Okay, but all the good thing is that it's an open-ended question, so different from the movie QA. Okay, also this movie chat. Movie chat is a new paper or a new model that is released in 2024, CVPR 2024, yes. And also this project is a concurrent project with Goldfish, because while implementing Goldfish, the authors only released 100 video from their data, okay? Because the movie chat project, they have the movie chat model, okay, and movie chat benchmark. But as they have a benchmark, as a workshop in CVPR 2024, the author said that they can't release their benchmark in March, okay, and only they released 100 video features from the training data. Okay, so this is not from the testing data, but only from the training data. But the good thing is that the average duration is 9.4, and they have an vision questions. Okay, this is the good thing. But TVQA-long, it has most of the benefits from these benchmarks, like it has the largest number of questions and largest number of videos. The average duration is 30 minutes, which is suitable for long video evaluation, and type of question is MCQ, and it contains both the vision questions and TV plot questions. So from this point, we can move to the mini-GPT video. Mini-GPT video is a video LLM that can process videos with duration 1 to 2 minutes. Okay, so given an input video, we will sample the video into multiple frames, and for to n frames, and for each frame, we will input the frame to the vision encoder, which is EvaClip model, to generate the visual tokens, and then we concatenate each 4 adjacent tokens together, okay, to compress the number of tokens. So we concatenated each 4 adjacent tokens together. Then we need to convert these tokens from the visual domain to the LLM domain. So we used as a linear layer to do this conversion. And by the way, this is the architecture of the mini GPT image version, has the same architecture. Okay, and also the idea of concatenation we inspired from the mini GPT image version. Okay, but here we are not also processing the visual frames, but also we have an interleaved input with the text, with the frame subtitle. Okay, so what is the frame subtitle? The frame subtitle is the dialogue that has been said between frame I and frame I plus 1. Okay, so we will input the frame subtitle to the text tokenizer to have the text tokens, and then for each frame we will concat the vision tokens and the text tokens together, and do this for the input frame. And finally, we input the user question to the text tokenizer, okay, to generate the text tokens and concatenate it with the video input, and train our whole architecture with the video data to generate or to answer the user question. Okay, so the trainable parts here are the large language model with LoRa to fuse these frames together and have a full understanding about the vision. And also we trained this linear layer to convert from the vision domain to the LLM domain. So what is that? What is the data sets, or what is the pipelines that we followed to train this this model? Okay, we have 3 stages. The first one is image text pairs, and we started from the mini GPT image version. Okay, so we didn't train it again, but we used the image version's weights, and then moved to the second stage, which is video text pairs. Okay, but we split it into 2 stages. The first one using video captions dataset, and second one is using a video instruction dataset. Okay, so we tried to exploit the datasets that is existing. Okay, however, this video caption dataset doesn't have a detailed captions. Okay, but it has an abstract captions. So we exploited this data during the pre-training stage. Okay, and finally we used high quality data, which is video instruct 100K. It is a high quality video instruction dataset that, and we trained it after the pre-training stage. Okay, and I know now there is a lot of new data sets more than this video instruct dataset, but while implementing this project, this is the only high quality one. Okay, and this dataset is from the video ChatGPT paper. So what is the evaluation metrics we used? So here, if you remember, we have 2 types of questions, like MCQ and open-ended. So how we evaluate them? So for the open-ended questions, we know that it's hard to evaluate the output from the LLM. Okay, so we followed the previous work to employ ChatGPT or a GPT model, GPT 3.5 Turbo, to compare between the generated results and the ground truths and give it a score. And we input GPT 3 saying the question and answer and the prediction. Okay, and for MCQ, we also used GPT 3.5, and that is because the open answer from the LLM, okay, we don't know what is the choice that the LLM choose between these inputted choices or the question choices. So we also asked ChatGPT or GPT 3.5 to decide if this open answer is one of the options or not. Okay. And here, this is MiniGPT for results. MiniGPT achieved the state-of-the-art results for 5 benchmarks like video ChatGPT benchmark. It is a benchmark that have 5 skills like information correctness, detailed orientation, and contextual understanding, temporal understanding, and consistency. And we achieved the state of the art here. Also here for the open-ended benchmarks like MSVD, QA, or MSR, VTT, TGIF, and ActivityNet and TVQA. We also achieved the state-of-the-art results here, but LlamaVid here achieved for activity only for ActivityNet. It is the state-of-the-art. So now ManyGPT can process short videos from 1 to 2 minutes. Okay, so how we can exploit this to understand long videos. Okay, so we did a training-free architecture to exploit ManyGPT video through an efficient retrieval mechanism to answer the user question. So how we did that? Given an input long video, okay, we will split it into multiple clips, M clips, okay, and for each clip, we will, by the way, each clip will be 1.5 minutes, okay, because 1.5 minutes means 45 frames. 1.5 minutes it means 45 frames at FPS half, okay. So this is the ideal input to ManyGPT video, because the maximum number of frames for ManyGPT video is 45 according to the limited context window of Llama 2, because the context window of Llama 2 is only 4K. Okay, so and each frame is about 64 tokens. Okay. So here, for each clip, we will input the clip to ManyGPT video and ask ManyGPT video to describe the video with a detailed description. Okay, so the input here will be the video plus subtitles, because ManyGPT accepts an interleaved input between the frames and the subtitles. And then we have an S1, which is a description. Okay. About which is a description about the video, and then we also then we will encode this description using a text encoder to store it as a TS1. TS1 is a vector embedding of the text description. We also will encode the subtitle of each clip, okay, to have a TU1, and we will do the same for the M clips. So whatever the video length, we will encode it with the same way and store these embeddings in the retrieval module. Finally, when the user have a question, we will encode this question with the same text encoder, and then measure the similarity between the text encoder or the user question and the stored embeddings to retrieve the most related clips, and then input these clips to the answer module to generate the final answer. Okay. And here, this is the Goldfish results. We have the results for 4 benchmarks: LlamaVid, MovieChat, MovieQA, and TVQA. And we can notice here, like, we achieved the state of the art in the vision modality. And with vision plus subtitles, okay, MT here means subtitles. So we also achieved the state of the art in TVQA benchmark, but here in LlamaVid benchmark and MovieQA, we didn't achieve the state of the art, but this is because here LlamaVid is trained on the LlamaVid data, because we split this validation from the training data. Okay, and here also MovieQA and LlamaVid, both of them share the same movies. Okay, so also the movies in MovieQA, LlamaVid saw it during the training, so this is also not a fair comparison. But for the zero-shot evaluation, none of them saw the TVQA videos before, so we achieved 41 and LlamaVid achieved only 26. Here, moving to the applications, we did a lot of applications. So first, we tried multiple text encoders, okay, and we found that OpenAI embedding is the better one, okay, for to store the embedding and retrieve. And by the way, how we measured this retrieval accuracy. Here, TVQA-long here contains a very good property, like because we know we aggregated the clips together. Okay, so we know that this question is from clip 1, this question is from clip 2, this question is from clip 3, and so on. So now when asking the Goldfish like this question, so we know that it should retrieve clip 3. Okay, so if the clip 3 is one of the retrieved clips, so it is a true retrieval, and if it's not, so it's a false retrieval. So we can measure the retrieval accuracy with TVQA. So moving to here, we noticed that the retrieval accuracy is 64 with OpenAI embedding, and we can notice here that there is a linear correlation between the retrieval accuracy and the overall accuracy, as when the retrieval accuracy improved, the overall accuracy improved. Also, for the answer module, we applied some applications. Okay, like now we know that is clip 3 and 5 and 6. These are the most related clips to the user question. So how we will proceed these clips? Okay, so we have an information about these clips. What is the information? Is we have the summary from the retrieval. Okay, and we can input this question again to ManyGPT to extract more information about the question. Okay, so the first application is to input, like we retrieve the clip 354 or 357. Okay, so we will input the summary and subtitle of clip 357 directly to the LLM with the question, and these summaries will be as a context from the video to help the LLM to answer the question. This is an option A. And option B is to, okay, we know the clips numbers, like 357. We will input these clips to ManyGPT again to extract more related information about the question, and then input this information with the summary and the question to the LLM to have the final answer. Okay, and the third option is to input the information and summary and the subtitle. It's the same as option 2, but we only added the subtitle here as a context. Okay, with the question. But it seems to be this option is the ideal one because we dive in or we investigate the retrieved clips more. But unfortunately, this is not the optimal one, but the first one is the optimal one. As here, this is the results. Like option A achieved 41, option B achieved 27, option C also achieved 27. Okay, and I will try to clarify why this happened. This happened because of the model's hallucination. And what I mean by model hallucination here is like in case of ManyGPT video, or in this case, when you have a question and this question is not related to the video, okay, and you ask this question to the video LLM, okay, so the ideal answer should be, I don't know, because the question is not related to the video, okay, but sometimes the question, the video LLM tries to answer the question even it's not related, okay. So we try to explore this experiment, okay, by this prompt, like from this video, extract the related information to this multiple choice question, and provide an explanation for your answer. And we added this to make it, to add some chain of thoughts, okay, to make it think and answer correctly. Okay, and if you don't know the answer, please say I don't know as an option 5, because maybe the question is not related to the video, and the question is your answer is. Okay, this is the input prompt. Okay, and let's imagine that this is the question: what is Joey is eating when Chandler is on the phone with a guy from his old job? The options are a piece of pie, a popcorn, a donut, a bread roll, and option 5, I don't know. And I added this option, okay, to, because I said in the prompt, you can choose I don't know if the question is not related to the video. Okay. So the answers will be something like this. Based on the video content, the correct answer is popcorn because blah, blah, blah. The second one, say clip 7, the correct answer is a bread roll because blah, blah, blah. Yeah, maybe clip 7 is the ground truth. Okay, so this one will be the correct one. Okay, so clip 12 will be, in this video, Joey is eating a donut because blah, blah, blah. So given this as a context to the LLM, so we have 3 options here, or the model choose the 3 options. Okay, so this is made a conflict to the LLM here to choose the good answer. Okay, but by providing the summary of the question of the video, okay, this is a valid context which makes the LLM can extract the answer from it. Okay, so that is why option A better than option B. So here, this is one qualitative result of the Goldfish framework. Like the question is, how many people were in the car when Phoebe is driving? These are the options. The car is empty, 5, 3, or 1. Okay. So here we can notice that the model, the answer is 3, and this is because there are 2 people in the back seat in one description, and one is driving. So we can infer that there are 2 people in the back seat, the man and the woman, and the person driving Phoebe makes it a total of 3 people in the car. Okay, so this is one qualitative result. And also, this is a qualitative results for many GPT video. Like this is an example for describe this video in detail. And by the way, this video is about a man or someone who is trying to drawing a tree. Okay, from the beginning, from the white paper to the final shape. Okay, and here this is a detailed description. So the summary of our paper contribution is a mini GPT video, which is a video LLM that is achieved state of the art for a video for the short video benchmarks like video chat GPT, MSVD, MSR, BTT, TGIF, and TVQA. And the Goldfish framework, which has a framework that is used a retrieval mechanism to split the long video into multiple clips, and then tries to answer the user question from only these clips. And we achieved the state of the art in the TVQA-long benchmark. And the third contribution is TVQA-long benchmark, which is the trick that we did to convert an existing short video benchmark from short video to long video understanding. Yeah, thank you. And your questions are welcome if you have questions.
Okay, Kirolos, I'll start off with a question I have in the chat. Give me one moment here. So I was curious, you had mentioned, in terms of the initial instruction data and training, linear video input was used. I'm curious, can Goldfish be adapted to nonlinear video as well.
What do you mean by that linear video?
Video clips that are broken up. So say, for example, instead of having one full scene, you know, where they're in the living room talking to each other, and maybe the scene is broken up. So one portion is the folks talking to each other, and then the next section, the next 10 seconds of the video could be they're outside riding in a car, and then it can go back to the living room. So that's what I mean by nonlinear, not a complete scene, but broken up into different scenes.
Yeah. This can be answered by Goldfish, as each clip will be have like the summary. You will have a summary with mini GPT, okay, and then store the summary in the retrieval module, and then with the question, the system will try to choose what is the related clips to this question, and then answer this question.
Ah, gotcha. Okay, makes sense. Okay. Let's see here. Hey, Dan, did I answer your question in the chat? I don't know, Dan. Yeah, Dan was just curious where he could see the presentations, and I went ahead and sent him the link to the Goldfish project site. Actually, I'm curious as well. While we're waiting for a couple more questions, KAUST, maybe you can show us the project site, because I noticed you and the team had quite a bit of interesting information there.
Okay, so open the project site.
Yes.
Website. Okay.
Yes. Yeah, you had a lot of interesting information there on the site. Sorry to put you on the spot for going to the internet.
No. Okay, that's here.
So yeah, I noticed you have the paper, you have code, and the data set as well.
Yes. This
so
is the data set.
Is the data set the latest data set that you have to date that was used to train both Goldfish and the mini GPT?
Yes, all of this information can be here in the code. In the README, I put the full instruction to how to download the data that is used during the training, and what is the data that have been used during the evaluation, and so on. And I put each link.
Okay,
yeah,
wonderful.
But this one is only for the new TVQA-long benchmark.
Okay, that sounds good. Okay. So before we went to the questions, Benedict, did you want to start off?
I do not have any questions today. It was very straightforward.
Okay.
It was very straightforward.
Okay. So I see we have a question from Sina. Sina, did you want to come off of mute to ask your question?
Yes. Hello. Thank you for your presentation. Very cool work. I was curious if you've considered, because I noticed that you had converted the videos to the text modality, and then used the similarity measure to kind of sort of calculate, like do the retrieval. Have you considered using cross encoders alternatively to feed the text like directly to a cross encoder instead of like embedding them using the API?
So you mean only using the subtitles?
As far as I'm in the video descriptor module, if I understood it correctly, you ended up with 2 text embeddings.
Yes.
Have you considered instead of like having your own retrieval module and like using a similarity measure, have you considered using cross encoders which are like fine-tuned specifically for relevance measuring and like feeding the text directly to the cross encoder instead of using like your own similarity measure?
What do you mean by cross encoder? Like
so
to encode the video, like cross encoder is the one like video encoder, okay? And this video encoder can. Yeah.
I mentioned it for the text because like we have bioencoders that like you have to give individual like text tokens to them and get the embeddings or representations and compare them yourself using your similarity measure.
Yes.
Or you could use a cross encoder to compare like two passages or sentences directly because it's fine-tuned for relevance measuring. Have you considered that?
If I understood your question correctly, so we measure the similarity between the embedding. Like I can't understand what exactly is this cross encoder.
If you could go to the framework, I could try to elaborate more.
Here.
Okay.
Yes, perfect.
Hey,
so,
Kirolos, could you make your screen a little bit bigger?
Yeah.
Okay. Okay,
perfect. So here you have like two text encoders that you use to give the embeddings to your retrieval module. If I understood it correctly, I might be wrong.
No, but this is shared. This text encoder is the same in the three dialects. This is shared.
Okay.
It's
a single encoder.
Yeah. This is not a different thing.
But it's an API, correct? Like in your.
Yeah. From ChatGPT.
So it comes with a cost. That's what I'm saying. Like you have to call the API for each description.
Yes.
So what I experienced in information retrieval is you have two options. You could get the encodings, like calling the API just the way you did, and compare them using your own similarity measure. But I think like an additional ablation study could be, instead of like sending them individually to an API to encode them for you, which comes with a cost basically, you could like use open source cross encoders that get the text directly. And the thing is, because they're fine-tuned for relevance generation, you could use like a smaller models, open source models with the same amount of effectiveness.
Okay. So you mean to, instead of measure the design similarity, to have a model to decide if these are relevant or not?
Exactly. I'm not familiar like with this specific task. I've worked for information retrieval, and when I use like bioencoders, using APIs and then comparing them myself, I needed a much more complex and expensive model than when I used a cross encoder, because it's fine-tuned for relevance measuring.
Yeah. Okay. Yeah, this is a good suggestion, and yeah, I can do that and put it in the applications to see what is the results of it.
Yeah, it sounds like that might be a chance for you guys maybe to work together on the. Yeah.
That would be awesome.
Okay.
Yeah.
So
thanks a lot, Stina. I like the idea you brought up. Thanks a lot.
Yeah.
Of course. Thank you, guys.
Yeah.
And I see we have a question, and I see your question as well, Miyak. We'll get to you in one moment, but I see we have a question from Ildar as well. Can you see that question in the chat, Kirolos, or do you want Ildar to come off mute?
Yeah, I see it. Given the multimodal approach frames plus subtitle and the integration of modules like Benedict and MiniGPT.
I don't think there is a module called Benedict in GPT, so I think that's probably a typo.
Yeah, maybe.
That's probably a typo.
Yes. The integration, like what specific challenges remain unresolved in improving the temporal and the contextual understanding of long picture, and how you plan to address them in the future iteration of the Goldfish frame. Okay, like one of the areas that can be improved in this project to solve this problem, like here we can notice that this option 2 is have a more sense. Okay, to if after retrieve of a question, so you should investigate them more and extract more information about the query, because the summaries are independent to the query. Okay, so the summaries may have the answer of the question, but sometimes the summary is a general description, and maybe the question needs a specific detail in the video. So option 2 is the best, okay, or should be the best. But we need to solve this model hallucination problem. And we can solve this problem with the model hallucination to train a model or make many GPT for video to train it with a negative data. Okay, like can understand if the question is related to the video or not. I think after doing this, maybe maybe option 2 will be better than option A and maybe exceed this 41 to be some 60 or 50 months. So this is one of the directions. And another thing is to think about long video understanding, or to move in this direction is try to solve the problem of limited context window. Okay, as nowadays also our group have a new project called Long VU. I'm not one of the authors of this project, but my friend Shaushan, she is a second author in this project, and she is the first author of the other project, Long VU, and she did an adaptive compression, okay, module to compress all of the tokens, okay, all the important tokens in the video and input it to the large language model. Yeah, this I think this are the two directions that can be the new step in this or after this project.
Okay.
Yeah.
Okay. And we have a question from Mayank as well.
Yeah. So hi. I wanted to ask. You utilized EVA clip here to integrate the projection layer to map visual features from the vision space to the text space. So why did you use only that, or you had other models in mind too, other encoders in mind too?
To change this EVA clip and try another image encoders? Unfortunately, I didn't did this application, but we exploited this vision encoder as, by the way, our team is the same team as that created MiniGPT image. So yes, we started and we exploited the training that we did in MiniGPT image, and then so we followed the same architecture to make it able to have understanding for videos. And yeah, we did that with the video by training it with interleaved with a video text data.
Oh, okay, cool. Plus, like, I had another query with respect to your training process. So you reduce the token count per image by 75%, like from 256 to 64, as in like some other works like that had appeared before. And you kind of, in the figure that you had shown that they generate each clip essential for conducting visual question on answering tasks in the vision language domain. So like, I was wondering, could you explain that process a bit? And like, how did you get that, the compression that you achieved?
Yeah. This is a good question. Okay. Okay. So here, this is the vision encoder. Okay, it tries to split the image into the vision tokens. It's pitches. Okay. And so what we did for the concatenation, so we concatenated like each token. Say maybe each token is 512. Okay, in the dimensionality. Okay. So what we did is we concatenated these tokens, each four adjacent tokens together. Okay, so the number or the vector dimension is 4 times 512. Okay, and we did that. Okay, we did this compression, and we found there is no loss in the performance of the whole architecture. Okay, like but we did this ablation in the MiniGPT image version. Okay, so we didn't repeat it again in this paper, but the authors of MiniGPT image version, they said that 4 is the best number, and by trying to concat more than 4 tokens, okay, the performance is decreased, and yeah, so 4 is the best number to decrease the number of tokens.
Oh, okay. Thanks.
Yeah, same.
Okay, I don't see any other questions in the chat. Last call for our attendees. Anyone else have any additional questions for KAUST? Okay, well, I think we're done, KAUST. We really appreciate your time today. This was an excellent presentation. Did you have something else you wanted to say, Benedict?
Nothing on my end. I just want to thank KAUST for taking the time to be with us today. Thank you for sharing your work with us. It's very appreciated. Yes. I'm sure we all learned quite a lot here today. I think Sina, his question really piqued my interest, right? He piqued my interest, and I think you should probably see about working with him on implementing cross-encoders with the project. That would be nice.
Yes.
Yeah. Sure.
Yes. So thank you very much for being here. Yeah.
Okay, well, thanks, everyone. Everyone have a good rest of your day and evening.